day of the pre-string school. So I'll be chairing the session this morning, and we will start with the last lecture by Tom on the information paradox. Go ahead, Tom.
All right. Welcome back, everyone. So let me recap where we are so far from the first two lectures. So the idea is that if black hole evaporation is unitary, if quantum gravity is ordinary quantum mechanics, then we have the unitary hypothesis about black holes and black hole evaporation, which just states that a black hole is an ordinary quantum system with a finite number of degrees of freedom. Now, that statement is enough to get a paradox. So there were some questions last time, and I wanted to clarify this. This statement that there's a finite number of degrees of freedom, this is enough. Now there's a paradox. Now, if we want to refine that statement a little bit and say that the number of degrees of freedom is given by the Bekenstein area law, area over 4, then we can understand in more detail exactly when the paradox arises and when we expect new effects to come in. But just having it finite is enough, because if you interact with a quantum system with a finite number of degrees of freedom, you cannot generate an arbitrarily large amount of entropy by those interactions. So that's what we're testing. And we worked out this example of the eternal black hole. Okay, so we have a region R, which is two disjoint, it's a union of disjoint regions on the left and right. And what we've done so far is to produce a paradox by calculating in the classic pre-islands way, the entropy of the Hawking radiation. We did that by the replica method. So we calculated these replica partition functions, trace of rho r to the n. Each of these spacetimes here is a Euclidean black hole, and these cuts correspond to region R, and the replicas are glued together along the cuts cyclically around the n copies. The way I described it last time, we did this calculation first in flat space and then turned on the conformal factor. And here I'm just summarizing it all together, where we just do this calculation directly in curved space. So we calculated the CFT partition function on this replica manifold. Then we took n to 1 and extracted the von Neumann entropy and found that it's growing linearly in time. In the RST model, it was n over 3 times t. The fact that this grows without bound gives us a paradox. So that's the paradox that we've generated, and now we're going to talk about non-perturbative corrections. A point that I want to make here, that I want to emphasize, that I don't know if I emphasized this last time, was that so these replica partition functions, you can think of as measures of entanglement of the region R with the black hole. In fact, these measures of entanglement are called Renyi entropies, and so this is a measure of entanglement with a name. The replica partition function is up to a factor e to the minus the Renyi entropy. And the fact that this entropy is growing linearly in T means that this entanglement is growing with T. So these saddle points that give the Hawking entropy are exponentially suppressed at late times, and they're being suppressed by entanglement. Okay, so I want to emphasize the role of entanglement here. It's the entanglement of the Hawking radiation with the black hole interior is causing these saddles to be exponentially suppressed. And that gives us some hope that maybe there are some new effects that come in and become important when that entropy is large. That is, when we see the paradox. Okay, and those are the effects that we're going to discuss now. Okay, so what I'm going to do is I'm going to finish this calculation we're going to finish the calculation, and then I'm going to go into some comments. I need to find my notes here, one sec. Okay, so now we're going to talk about the wormhole contributions, and that'll lead us to the idea of entanglement islands. So the claim here is simple. The claim is that when we did this calculation last time, we missed a saddle. You can think of this as a sort of instanton contribution to the path integral that we haven't included. I'm going to illustrate this with the case of n equals 2 replicas. So for n equals 2 replicas, we're calculating trace of rho r squared. And when we did that calculation last time, we just included a saddle that looks like the one on the previous page. Okay, so there were 2 copies of the Euclidean black hole glued together along region R. But when I describe this calculation this way, it's clear that there's another thing that we should consider, another topology that we should consider in the calculation of the path integral. And that is the connected topology. That looks like this. Again, we have things glued together along region R. So this is a pretty complicated manifold. It's glued along these branch cuts and joined in the black hole interior, or rather the throat of the Euclidean black hole. So this first one I think of as the Hawking saddle, because it gave us Hawking's calculation of the entropy. And the second one is called a replica wormhole. It's a space-time wormhole joining the different replicas. So let me make a comment about path integrals and quantum gravity in general, because this is really what makes it so different from doing path integrals in quantum field theory. In quantum field theory, we specify the geometry, and then we do the path integral on the geometry. But we don't have that option in quantum gravity. In quantum gravity, what we do is we specify the boundary conditions on the geometry. And then we have to sum over manifolds that satisfy those boundary conditions. Okay, so that's what's being done here. Is we're really not specifying the geometry, we're specifying the boundary conditions. In this case, the boundary conditions correspond to this geometry here that's far outside of the black hole throat. So the boundary conditions are like this piece of the geometry. I guess I should have drawn these tubes as being longer. We're thinking of these regions as being very far from the black hole. So this part's the part that's boxed here, that's the asymptotics of the geometry. And what we are supposed to do in the gravitational path integral is to specify this asymptotic geometry and then do the path integral with that boundary condition. When we do that, we should include that, well, it's up to the gravitational equations of motion to tell us what the saddle points are. And this geometry over here, the replica wormhole, has exactly the same boundary conditions. So there's no reason not to include it. Now, we still have to look for saddle points. Okay, so there's no guarantee that this will contribute anything non-zero or large to the path integral. To do that, we have to do the path integral, or we have to calculate it in the semi-classical approximation by looking for saddle points. Okay, but I claim, and we're going to understand in a few minutes, that there are saddle points that look like this, and we can calculate them. And what that's going to do is it's going to give us a second contribution to the replica partition function. So then the total semi-classical approximation to the path integral is a Hawking contribution plus a wormhole contribution, and potentially plus other ... And the important thing here is that this term, as we were just discussing, this term is exponentially suppressed when the Hawking radiation is highly entangled with the black hole. So this is exponentially suppressed at late times. Suppressed by large entanglement. The wormhole term well, we're going to calculate it, and what turns out the way it works out is that this is suppressed by the topology, the fact that it has higher topology. The way to think about that is that there's some gravitational contribution that goes as 1 over g Newton. So there's some gravitational contribution to the action of this wormhole that's going to cause it to be exponentially suppressed. However, that suppression is constant in time. Okay, so there's a fixed exponential suppression of this wormhole contribution. So when you put this together, what it means is that at early times, the Hawking saddle is going to dominate. But eventually, this one is going to be so exponentially suppressed from the entanglement that the wormhole saddle is going to take over. So that's the basic idea of replica wormholes. Now, to calculate the von Neumann entropy, we have to be able to talk about replica wormholes at all values of n, so that we can analytically continue n to 1 to get the von Neumann entropy. You can find these wormholes at higher n's. They're going to look something like this, for example, at n equals 3. And you can draw similar wormholes at higher n. But what we really need to do is to analytically continue to non-integer n. And we do that as follows. So we assume a Zn cyclic symmetry that permutes the replicas. Okay, so we assume, like in this picture that I've drawn, that it's symmetric under these Z3 rotations. Okay, there's a question. Go ahead, Aswin.
Yeah, so can't we have genus contribution? So there is no hole in the topology that you have drawn. So can we have some genus contribution?
Yeah, a contribution like this?
Yeah.
Yeah, we could have contributions like that. What I'm about to describe allows for those contributions as long as they're Zn symmetric. And what those would correspond to when we get to the island rule is disconnected islands. If you have an island, say, with 2 disconnected pieces. So I'm not going to discuss that possibility, but that is included in this formalism. Okay, so as long as we have that Zn symmetry. So let me erase that handle and tell you, how does this help to assume the Zn symmetry? So the answer is that if we assume that symmetry, then I can draw here, I can sort of split this into 3 pieces by cutting the wormhole like this. So that's supposed to cut this wormhole into 3 pieces that are symmetric under the Z3 rotation. And once we've done that, we can go to the quotient manifold. So we take the replica manifold Mn, and we go to the quotient Mn mod Zn. Now, this quotient manifold has the following topology. So the point is that we're now going to view the quotient manifold as a branched cover of the Euclidean black hole. So here's my Euclidean black hole. We have these branch cuts in region R, one on this side of the black hole and one on the far side of the black hole. But this is not the topology we want. This is the Hawking topology. We can get the topology we want by putting in an additional branch cut. Okay, so this branch cut goes deep inside the black hole and goes around through the Euclidean horizon, which is the tip here. Okay, so what I'm claiming, and this really takes a couple minutes of staring at the pictures to convince yourself that this is true, but what I'm claiming is that this replica manifold, so if you take one of these replica manifolds and take the quotient, that it looks like a branched cover of the original Euclidean black hole, just with some extra branch points. The way you should think about this is that if you go through the branch cut here in the tip, then you land in one of the other copies of the black hole. So if I do this in these pictures, then actually these red lines here that are chopping up the wormhole into three pieces, that corresponds to this branch cut. So for example, if we're walking along this manifold and we hit the branch cut and go through, then we land on a second copy of the wormhole. And that would correspond in this picture up here, that would correspond to walking along on one copy of the black hole, you hit the branch cut, and you walk right through and come out in one of the other copies. Now, in this picture, sorry, there's a question. Go ahead, Antonio.
Hi. So what about contributions that are wormholes between some copies but disconnected in the other, and then one can add permutations to make them ZN invariant? No, probably just permutation invariant, but not ZN invariant. Is that the point? Or?
Well, you can always symmetrize any contribution, but I'm really talking about individual saddles that are ZN symmetric. Some of those, it would be, some of those other saddle points can be included and are understood. And what they do is they give you subleading contributions to the page curve. But I'm just going to focus here on the leading term. We think this is the leading term. I should mention that if we miss something in this calculation, like these dots, if there's some additional saddles that I haven't included, then that will only make the paradox even better, because we're already going to get unitary entropy from this wormhole contribution, and the only thing these dots can do is make the entropy even smaller and even more compatible with unitarity, and so it could potentially, these dots could potentially change the page curve, but they won't change the fact that we're going to get a unitary page curve.
Thank you.
Okay, so when I draw this picture, it's important to point out that I'm only drawing for you the topology. Okay, I'm not saying there's a flat metric on this topology. In fact, the metric is not flat at all. The metric is whatever it needs to be to solve the Einstein equations on the replica manifold. And in particular, let's think about these branch points here. When we talked about the replica trick in conformal field theory, the branch points were conical excesses. That was in quantum field theory. In quantum gravity, they are not conical excesses, they are smooth. These are smooth points on the replica manifold M sub n. What that means in terms of the metric near those points is that locally, the metric is 1 over n squared z to the 2 over n minus 2 dz bar. And I'll make it an exercise to check that this metric means that it's smooth. What I mean by that is that around this branch point, z is identified with a circle of size 2 pi n. Because as we go around these branch cuts, we go around on the n sheets of the replica manifold. We have to go around n times to get back where we started. Okay, so if you have a coordinate that's identified on a circle of size 2 pi n, I claim that this is the smooth metric. Okay, and you can check that by doing a coordinate change to put these into just an ordinary flat coordinate. So why is it smooth? Well, that's just because we're doing gravity and we're looking at saddles. So the gravitational equations of motion will smooth out this point. A conical excess does not solve Einstein's equations. So it will always be smoothed out just by the gravitational back reaction. In terms of the entropy that's going to come out of this calculation, the smoothness of this twist point will not have a UV divergence. The entropy will not have a UV divergence from this twist point because it's smooth. If you remember from last time, when we discussed the entanglement entropy calculation in conformal field theory, we found a UV divergence from the conical excess at the twist defect. Now there is no twist defect. Gravitational back reaction is curing that defect. So there's no divergence, there's no need to regulate, and we'll just get a finite answer from that, a finite contribution from that point. Okay. Now, sorry, there's a few questions. Bauer?
Hi, Tom. I just want to ask, is gravity fluctuating in the region R?
No. So what I'm doing here is using large N in the matter sector so that we can ignore the graviton contribution in region R and just freezing that part of the metric. If we wanted to apply this, so that's completely correct, say in the RST model or in JT coupled to large N matter. If we wanted to apply this, say, to the Schwarzschild black hole in the real world, then we would have to understand how to deal with those graviton contributions around region R.
Just where is the transition between the gravitating region and non-gravitating region here?
The way that I think about this, I would say that this is a subtlety that's not been totally understood, but the way I think about it is the following. When we do this calculation with region R at a finite distance from the black hole, it doesn't quite make sense because, as you say, gravity is fluctuating there, and it's not really a boundary condition if we impose the metric at some finite distance from the black hole. So that's not really allowed. But eventually we're going to take region R to be up on Scri plus in the asymptotic region. And then I think when we take that limit, I think it becomes correct to think of this as a region and to think of this, of imposing the metric there as a boundary condition. But I think that there's subtleties there having to do with the fact that gravitons can reach Scri plus, and those subtleties have not been totally understood.
Okay, so we just imagine that corrections are suppressed by the fact that the region is far from the
That's right. That's right. There could be extra perturbative contributions there, but I don't expect any strong gravitational effects out there, so I don't think it can give a large contribution to really change the story. Tushar?
So in MN, we take, let's say, multiple boundary conditions, and then we solve Einstein's field equation, for example, which gives us a smooth geometry. Now, when we take this quotient manifold, that gives us only one, let's say, boundary thermal circle. And similarly, when we solve Einstein's field equation, I understand that we will get a smooth geometry and not a conical defect. But then in this quotient manifold, why are we getting this branch cut? Can you just explain that again? I mean, yeah, it's similar to the QFT case, but yeah.
Yeah, so I'm really just describing this manifold here as a branched cover of this manifold. And these are the same manifold. I'm just saying that we can think of this one as being a branched cover of this one. That's the point. And did that answer your question?
Yeah, just gluing together these copies, but you're saying that instead of having a conical defect here, it will smooth out.
Yeah, that's right. That's right. On this manifold, it's easy to see that these points are smooth. The twist points are just the fixed points of the quotient, which are these 2 points here on this side and the far side. So it's very easy in this picture to see that we're talking about a smooth manifold with the twist points. But when you write that as a branched cover, that means that you have to put this funny metric on that quotient space.
I see. And yeah, okay. I mean, okay, thank you. Yeah.
Pablo?
Yeah, I was wondering, does the Zn symmetry on the replica manifold fix the position of these new branch points? Because you stressed in the cigar picture that they are far, so they're near the horizon. They're definitely far away from the 2 points that we have from our region. Or does it actually play a role, or is their position fixed by the Zn symmetry when I look at it in the other picture?
Let's see. In this, well, okay, position is a bit tricky because we're doing gravity and we can, so there's position in the coordinate sense and there's the physical position in the physical sense. Okay, so the geometry on here has not been fixed. We have to solve the equations of motion to find the metric. Now the twist points will always show up here and here, but there's a funny metric. There's a metric on this manifold that we have to solve for. So in this picture, you should think of the endpoints of this region as being determined dynamically by solving the equations of motion. These twist points out here, these are just like the twist points of our CFT calculation in the second lecture. So these ones are fixed. They have conical excesses. They're just like the CFT calculation. But these ones, their position is going to depend on solving the equations of motion, and they're going to be smooth.
Okay, yeah, right. Thank you.
Okay. So let me sketch what happens now as we take n to 1. And let me go back a second. So now that we're talking about this quotient manifold, I can take n to be non-integer. Because all I have to do is look at this boundary condition at the twist points and just take n to not be an integer. There's no problem with that. Okay, so in the language of, that's the advantage of going to the quotient manifold. It's that we can now very easily analytically continue to non-integer n. If we allowed non-replica symmetric contributions, I would have no idea how to do that analytic continuation. But as long as it's symmetric, this is trivial. We just look in the boundary conditions at the twist point and put in whatever n we please. So now we can take n near 1, and I'll only have time to sketch this calculation, but I want to give a flavor for how this gives a new formula for the entropy. So we need to calculate the partition function on this manifold. So we're now calculating the partition function on the manifold that I just drew. You can write this in the following way. It's an integral over moduli. These moduli correspond to the location of region I. I forgot to name region I. Let me go back up. So this new branch cut, the dynamical branch cut, I'm going to call region I. Okay, so the moduli are the locations of the twist points. As we were just discussing, those are determined dynamically, and in the path integral, we have to integrate over them. For a fixed value, so now for a fixed value of the moduli, we can calculate the gravitational contribution to the partition function and the CFT contribution to the partition function. Those are both functions of the moduli. I've just separated out the path integral into an integral over moduli and the contributions at fixed moduli for everything else. Now I want to talk about each of these terms. So ZCFT, and this is going to be the crucial, this is going to be sort of the crucial step here. ZCFT is, so the way to think about ZCFT is we fix this manifold, and then we calculate the CFT partition function on this fixed manifold. Well, if you think back to our calculation in the second lecture, that's exactly what we would do if we were calculating the CFT entropy, but not the CFT entropy on region R, the CFT entropy on region R union I, because there are two branch cuts on this manifold. Okay, so what that means is that ZCFT is well, let me write it this way: trace of rho R rho CFT R union I to the n and that means that as we take n to 1, ZCFT will be e to the, let me get my sign right here, e to the n minus 1 times the CFT entropy. But it's the CFT entropy not on region R, but on region R union I. In this last equation, I've just used the fact that I've just used the relationship, the ordinary relationship between replica partition functions and entropies in quantum field theory. Okay, so that's the CFT contribution. Now let's talk about Z-grav. So I won't have time to do the calculation of Z-grav, but it's a fairly standard calculation. Let me write the answer. It only has a contribution from the area. This is actually Gibbons and Hawking's calculation of the black hole entropy, essentially. And so what it's going to give is the gravitational contribution to the entropy. The area here is the area corresponding to those dynamical branch points at the boundary of region I. The nicest reference I know of for this calculation is the paper of Lefkowitz and Maldacena on generalized entropy. So I'm going to have to refer you there for the details of that calculation. But putting these pieces together, what this means is that we have an integral over moduli of, well, let me write the formula in here. So these pieces together are exponential well, there's a contribution that there's a contribution at n equals 1, which is just replicated n times. And what I've been writing are just the order n minus 1 terms. So there's an n minus 1 times S gen of R union I, where S gen of R union I is 1/4 the area of DI plus SCFT of R union I. So that's what we just derived. And the last step then is to do this integral over moduli. And that just corresponds to finding the saddle points of this effective action. So the statement is that the effective action is the generalized entropy. And now we have to find the saddle points of that effective action in order to calculate the von Neumann entropy. So now putting this all together, we have our final answer. So let me write the formula. So the final formula is obtained by 1 minus n dn log Zn at n equals 1. And what we just argued is that this is, well, I'll write it first, min x I S gen of R union I, where S gen is 1/4 the area of DI plus SCFT of R union I. Okay, let's put a big box around this one. This is called the island formula, and it was postulated prior to replica wormholes based on arguments from holography and later derived. So I've done it in the other order just because now that we know where it comes from, it's easier to think about the wormholes first, and the island rule is a consequence of including these wormholes in the action. So let me explain this this min x here. So what's going on here is that the extremum over I, that comes from integrating over these moduli. That in our case, it's the location of the twist points. This final minimization here is in case there are multiple extrema. So if they're different extrema, we want to pick the dominant contribution to the action. So that'll be the one with minimal entropy. Okay, so we first find all the extrema, we calculate these S gens at the extrema, and then we pick the one with minimal entropy. Okay, so that was really the main thing that we wanted to calculate coming out of these wormholes. The last calculation, the last thing we want to do is go back and apply this formula to our black hole and see what happens. So I have pre-drawn this picture. If you're taking notes, now is a good time to stop taking notes because I've pre-drawn a couple things to make sure we can finish on time. So stop taking notes and just listen, and these notes will be posted, and you'll be able to find the figures on the video. Okay, so the application, so now what we're going to do is apply this to our black hole. And for these purposes, when I was saying area over 4, as we talked about, in dilaton gravity, the area really means the dilaton. So for this black hole, the area term is the dilaton, and there's also a contribution from the conformal factor. The CFT entropy on I union R. The easiest way to think about this is actually is not to think about I union R, but to think about the complement. Okay, so let me draw the complement region on here. There's a piece here, B. So I don't know if you can see where I'm writing. I'm writing right here. And then there's a piece on this side. So there's a B on each side. So the quantum fields are pure on the full Cauchy slice. So this is equal to SCFT of B. That is actually approximately 2 SCFT of the B on the right. The reason for that, well, this is true at late times. The intuitive reason for that is that at late times, the Einstein-Rosen bridge is very long, so these regions are very far apart, so the entropy just factorizes. You can also see this from an OPE argument for the twist operators. Okay, so I'm not going to work through the algebra, but you now have all the pieces in place here. We have the formula for the area. We have the formula for SCFT. This is just the CFT formula that we derived last time. And we just plug in, extremize, plug into SGen, that is, extremize, and what you find is that SGen, well, what you find is that there is an extremum, so there is an island, and the contribution to SGen, including the island, is a constant. So we can now go back to our page curve. And it looks like this at early times. That's the calculation that we did last time. No wormholes, it's growing with T. But instead of growing linearly forever, there's this second saddle. The second saddle has a constant in time contribution. And dominates the calculation of the entropy as soon as these two lines cross. So our final answer for S of rho r, as calculated by the replica method, is this curve that grows and then saturates at a constant for all time, and in particular is compatible with this unitary hypothesis that black holes are just ordinary quantum mechanical systems with some finite number of degrees of freedom. As I described, the contribution to the partition function is a sum of terms. And so what's happening in these two different, so what's happening at this transition point here which is called the page transition, is that these two saddle points are exchanging dominance, much like a phase transition. There's actually something that people talk about sometimes in condensed matter called a dynamical phase transition, which is something where this happens as a function of time as opposed to some other external variable. And this effect is very much like a dynamical phase transition. Okay, I have only 5 minutes left. So luckily I've pre-written some comments here. I just want to go through them. I'm going to postpone all discussion on this comments to the discussion session for this afternoon, but I want to make the comments now, and then we can discuss later because I have to stop strictly in 5 minutes. Okay, so these comments are on the interpretation. First of all, the ideas of entanglement wedge reconstruction in holographic duality suggest the following interpretation of the island. When the island appears, region I is now suddenly encoded in the density matrix of the Hawking radiation rho sub r. This is similar to subregion duality in ADS-CFT. It's almost like a holographic duality. What do I mean by encoded? Well, if we're collecting the Hawking radiation up here in region R, then at early times there's no island, but eventually we collect enough radiation that we see an island, and you can use that to answer questions like, for example, if I drop in a book into the black hole, when do I, in principle, have access to the book? Well, the answer is that you have access to the book when your island contains the book. And you could do this calculation quantitatively, and it agrees perfectly with earlier arguments, for example, by Susskind and Preskill and Hayden and others on the fast scrambling hypothesis of black holes. This is something, this encoding in the radiation of the island in the radiation is really the most fascinating part of this. It goes beyond just calculating, it goes beyond just the information paradox and calculating the entropy. It's really getting at how we think about black hole interiors in quantum gravity. So that's why people are so obsessed with the information paradox. It's not because they care obsessively about Hawking radiation. It's because it forces you to think about the interior of the black hole completely differently. And it's telling us quantitatively how and when we have to think about that interior of the black hole as being encoded in the radiation. So that's really where people's minds are now in trying to understand this. Another comment. Did we actually calculate the entropy? Well, that's not a comment, that's a question. Well, the entropy, as I defined it at the very beginning, is a trace, minus trace of rho log rho. And nowhere in this calculation did we ever do a trace of anything. So not exactly, no. We claim to have calculated the left-hand side in the low energy effective theory of gravity coupled to matter. But in this effective field theory, we cannot calculate rho sub r, the matrix elements of the giant, rho sub r is a giant matrix of size e to the s by e to the s, and we cannot calculate it. We cannot calculate it accurately enough to reliably calculate this trace. Not even in principle in the low energy theory. So the way to think about what Hawking told us in the original explanation of the paradox is that, well, we have to be careful about when it's reliable. And what he really told us is that there's a thermal contribution and perturbative contributions and some unknown non-perturbative contributions. So the surprise of these recent developments is that the low energy theory, well, this is not the surprise. Sorry, this is the background. The low energy theory cannot calculate these e to the minus s corrections to the matrix elements of rho sub r, even in principle. the surprise is that it can calculate the unitary von Neumann entropy showing up in the page curve. So the surprise is that even though the low energy theory doesn't know about these non-perturbative effects, or it doesn't know about them in detail, it knows enough about them in order to be able to see the unitary page curve. So that's both the surprise and the interest, why this whole thing is so interesting. So in particular, I want to emphasize that the Lorentzian interpretation of the evaporation process is still not understood. I've done a Euclidean calculation with a Euclidean path integral, and we believe it gives the correct answer, but it doesn't tell us the details about the density matrix or how the information dynamically in real time actually escaped from the black hole. This process must be, in some sense, a little bit non-local, but only non-local. It's non-local in a very mild way, exactly the way that we would expect in a theory of quantum gravity. That is, that geometry makes sense semi-classically, but that there could be large fluctuations in the geometry and non-perturbative effects that don't really respect the semi-classical, but the ideas that you would have from looking just at the semi-classical background. Okay, so we'll have time for discussing all these points later. Let me end by just, there was one more, the factorization paradox. We're gonna have to talk about that one in the afternoon. So let me just skip by it. And I will end just by leaving these references up here so that you have them on the video for more reading and to see where some of the details of these calculations are that I worked out. Okay, thanks everyone.
Thank you very much, Tom. Let's give him a round of applause quickly because he really has to go.
All right, see you in the afternoon.
See you, Tom. Thank you.